So we're going to calculate the change in Gibbs free energy for this reaction as written from left to right. One of the half reactions is given for us. It's not a simpler one because it's not just the metals, but we can see what's left. Silver is going from neutral to charged, +1. And for that to happen, there needs to be an electron being given off. And I could tell by looking up here, I see these 4s, but if I weren't given that, I would need to make sure that these are balanced. In other words, I can see that this second reaction, I need to have 4 of them go so that the number of electrons given off by the silver are the same as the electrons taken up in the top reaction. So note, that's something we will need. We note in the reaction as written, the number of electrons that is transferred is 4. Okay, we're going to need to know the cell potential, which means I need to know the oxidation potential of this reaction. If I look on my chart, I can see that I have silver here, but this reaction that's given is not oxidation, that's a reduction. So that means that I need to change the sign of this number to get my oxidation potential. Okay, so now I have my potentials of my half reactions. I can get my cell potential. And I see this comes out to be a positive number. That means it's spontaneous. That means that this reaction can do work. It will run an electrical current. So let's get to our equation for Gibbs free energy. Since we already said the reaction is spontaneous, we're going to expect this number for Gibbs free energy to come out negative because cell potential positive is spontaneous, change in Gibbs free energy that is negative is spontaneous. So when I plug in, that number n is what we said before is 4 at the top. It's the number of electrons transferred. Okay, and the units do work out. Something you would have to use is that a coulomb times a volt equals a joule. Okay, and so our Gibbs free energy did come out negative, like we said, and this is spontaneous.